Hello, everyone. This is Elisa Baum. I'm GridGain's Director of Product Marketing. We'll begin in just a moment, but first I need to conduct a bit of housekeeping. Could you please raise your hand using the hand icon located in the GoToWebinar control panel to let me know that you can hear me? Let's see here. Oh, I see hands. Thank you very much. Next, during this webinar, you will be on mute. Should you have any questions during the discussion, go ahead and enter them in the questions field within the control panel. At the end of the webinar, we will take time to answer as many questions as possible. And in addition, I will make sure that you receive a recording of this webinar and the slides within 48 hours. I'd like to thank you for attending today's webinar, Better Together, Apache Spark and Apache Ignite. It's being presented by GridGain founder and chairman of the Apache Ignite Chairman Committee, and he's also our Chief Product Officer, Dmitriy Setrakyan. In addition, Valentin Kolichenko, who is GridGain's lead architect, will be doing the demo portion of the presentation. And with that said, I'll turn the floor over to Dmitry. Go ahead, Dmitry.
Thanks, Alyssa. Hello, everyone. Thanks for attending. So today's webinar is going to be on the subject of Better Together, Apache Ignite and Apache Spark. So essentially, we'll be talking about the integration between Apache Ignite and Apache Spark and how they can be used together, what value do these projects add to each other, how one makes another better. And we'll also go over some Ignite features, given that I'm one of the Ignite commuters and PMC members. I want to share some Ignite features with you as well. And towards the end, we'll talk about Spark integration, and how various ways you can actually integrate Ignite with Spark and Hadoop. And then Valentin will do a demo with SQL using Apache Zeppelin visual interface. So it's going to be fun. Please feel free to write down your questions and we'll answer them towards the end. All right, so before I start, just to let you know, if you want to get involved in a very interesting project, we at Apache Ignite are always looking for the new community members and new developers, new commuters. Apache Ignite itself is a very fun project to work with. If you want to find out learn more about distributed technologies, if you want to learn how clustering works, networking, various networking protocols, various cache consistency protocols, etc., etc. All these tasks are available within Apache Ignite, and it's very easy to get started. You can just come to the Ignite website and check out our contribute page and our wiki. It has a lot of instructions, so hope to see you there. So before we start, again, my first slide, I always like to go over what Apache Ignite is, what an in-memory data fabric is. So if I had to describe what in-memory data fabric is in one sentence, I mean, the main goal is to improve performance and scalability of user applications. So by itself, in-memory data fabric slides in between your database and application layer, and it provides performance and scalability to your application. We do that by actually providing multiple components. All these components are in memory, and all of them can be used independently or together. But in one way or another, they'll make your application scale better or perform better. One of the main components we have is a DataGrid, which is essentially all about distributed cache, distributed transactions, distributed SQL queries. But despite that, it's one of the biggest components. It's just one of the components we provide. Probably the second biggest component would be compute and clustering components. We also provide streaming component. We also have service grid. We provide Hadoop acceleration, Spark integration, etc., etc. Main thing to note here is that you're free to keep using your own database when working with Ignite. We do not require you to replace your database, even though you can choose later on to use Ignite as a primary system of records. You do not have to. So if you have your MySQL data in MySQL, Oracle, Microsoft SQL, databases, you can keep using them, and you will not have to change your schema or your and even potentially your queries. All of that will remain the same. The project comes as a one zip file, so it's very easy to install. You unzip it, and you can start multiple nodes on the same server, and they will automatically discover each other with zero configuration. So it's very easy to get started with. It comes with numerous examples, so you can actually take a look at how various stuff is implemented and can be used in Ignite. It only has one mandatory dependency, which is on JCache APIs, because Ignite implements JCache standard, JSR 107. Other than that, you should feel free to add more dependencies as you go. If you need to use log4j, for example, for login, you would add log4j dependency. If you want to use Spring for configuration, XML configuration, that is, you can add Spring dependency, etc. But all these dependencies are optional. And finally, there are no hardware requirements. You can will gladly consume all the resources you make available to us. Essentially, if you have a small server with maybe 4 cores and 8 gigs, or a large server with 64 cores and maybe 500 gigs, Ignite can be deployed virtually with minimum configuration changes, and will take advantage of all the resources you make available to the to Ignite process. This jigsaw puzzle represents most of the components available in Apache Ignite. However, it's not an exhaustive list. It actually lists the main components, as I mentioned: DataGrid, Compute Grid, Service Grid. We also provide streaming. We have Hadoop acceleration, and under Hadoop acceleration, we imply Ignite in-memory file system, which is compliant with HDFS, and we also have Spark integration, which provides RDDs for Spark as well. So before we actually get into some features available in Ignite and how Ignite can integrate with Spark, let's actually talk about why we need to share state in Spark. How can Spark benefit from sharing state? So Spark, as we know, does not store data. It actually processes data. So in order to process data, it needs to load this data from some external storage. And that storage can be any distributed file system, or maybe distributed key value store, maybe HDFS, maybe Cassandra, etc. So once the jobs are running, once the data is loaded, the jobs can start executing on that data. However, upon completion of those jobs, the data is discarded because there's essentially no way to store it and share it between various jobs and applications in Spark without having some common data storage medium. In this case, it would still be HDFS or some key value database or anything, or maybe SQL relational database, etc. So in order for one job to pass state to another, you actually would have to store it to disk. This means that you would need to convert your tuples into a file format, and essentially requires serialization, deserialization, and actually it requires I/O because you now need to bring it to disk, which is not very convenient. And what Ignite actually, the integration Ignite provides with Spark is ability to share RDDs in memory. Essentially, RDD becomes a wrapper around Ignite caches, and you can use native Spark APIs when working with IgniteRDDs, but at the same time, RDDs in Ignite are mutable, and they allow you to, in addition to all the Spark operations, they also allow you to share state in memory. Ignite, and we'll talk about various deployment models as we progress through the deck, but essentially that's the nature of the integration. Shared RDDs that Ignite can provide to Spark in memory, and ability to pass state from one job or from one application to another. So how do we do it? How did we implement this feature? We implemented on top of DataGrid, which, as I said already, one of our main components. And why did we choose DataGrid as a backbone for this type of integration? Mainly because DataGrid natively supports key value store, key value API, I'm sorry, and that makes it a natural candidate for storing tuples. On top of that, DataGrid already has SQL and indexing capability built in, and that actually allows us not only share state within across multiple jobs in Spark, but additionally actually allows us to provide faster SQL. So if you use IgniteRDDs, which are essentially working on top of a Ignite DataGrid. So if you use IgniteRDDs, you can run SQL using those RDDs, and the SQL will run a lot faster in Ignite than it will in Spark, simply because Ignite has in-memory indexes. So we index data, Spark doesn't. There's everything else is there's no magic to everything else. If you do indexes, your SQL will become faster. So in Ignite, we support all sorts of indexes, from basic field indexes, primary key indexes, to compound indexes, ordered indexes, etc. So fairly rich indexing capabilities in Ignite. All right, so let's actually take a look at some of the features available in Ignite that are relevant for that are very relevant for Spark integration. One is our in-memory data layer, which is implemented within DataGrid. And if you look at a DataGrid, what it provides you is the main capability it provides you probably is ability to talk to your data in multiple ways. So as a native API, as one of the first APIs we have, we supported in Ignite was the key value store, key value API, which was based on JCache GSR 107. So we chose that API simply because it was very user-friendly and very easy to learn. If you know how to use concurrent map from Java, you'll probably see a lot of similarities with JCache API. So JCache just added a few exceptions because most operations are distributed in nature. So you need to have a notion of error handling built into your API. But other than that, you will notice that it's very similar to Java concurrent map API. So it provides you basic put, get, remove abstractions, also put if absent, replace operations. It also allows you to collocate your processing with data by sending basic closures, basic entry processor closures to the nodes where the data resides. So if you know in advance which key you're operating on, you can send your computation directly to the node where the data is. And it also provides integration with the data layer. However, it's important to note that JCache spec on its own does not have any distribution built into it. So if you look at the API, you could use it locally or locally for local caches or for distributed caches. So for distributed caches, actually, proper support for distributed caches, you need a lot more than just basic key value API. And that's where Ignite DataGrid comes in with additional functionality. I mean, probably the main one will be the two main features that DataGrid adds would be transactions and SQL support. So Ignite is fully asset compliant. It may not be as important for analytics, but it becomes very important when you do analytics over operational data, for example. Or it becomes very important for transactional processing on top of Ignite. So the data is not eventually consistent. The data is not sometimes consistent or consistent after a certain period of time. In Ignite, data is always consistent, regardless of the topology changes. A lot of users in Ignite come from financial background, And Ignite is being used there for literally moving money between different applications or or as a result of various business operations. And when it comes to money, you have to be always consistent. You cannot afford to be even a little bit inconsistent. Another feature that DataGrid provides is full SQL support. Ignite is probably the only, or one of the very few, if not the only DataGrid that provides full ANSI 99 support for SQL, including full support for indexes. Very important that indexes are supported, and indexes are also always consistent. Essentially, if you're storing hundreds of gigabytes of data in memory, doing full scans, in the absence of indexes, you would have to do full scans, and that would actually potentially take minutes. Once you add indexes, the operations takes milliseconds. So it's almost instantaneous. And I hope Valentin at the end of this presentation will be able to demonstrate that. There's also support for on-heap and off-heap. And off-heap essentially allows you to avoid all the garbage collection issues that we're so familiar with in Java. If you use off-heap memory, Java JVM will not know about it, and therefore garbage collection will not be affected. And as I mentioned before, there is also RDBMS, automatic RDBMS integration. We do not require that you change a single line of code or single anything, single element in your database schema. So we'll integrate with your existing database schema. And if you use Ignite Web Console, we'll actually help you automatically generate all the domain classes and do some basic OR mapping. So you don't even have to write a single line of code when integrating between Ignite and the database. All right, so this how actually the data gets distributed in Ignite. There are two types of caches, partitioned and replicated. Replicated cache will usually will always have a copy of data on every server. So you can only cache as much data as can fit on one server. If you look at this diagram, then you see that all keys are available on all the servers. Every server has A, B, C, D, all 4 copies. The disadvantage of this approach is that every time you make a change, every time you make an update, you have to go to all 4 servers and update them. So the more servers you have, the more expensive an update is. Not very scalable from update standpoint, so if you have frequent updates, you should not use this type of cache. However, if you do reads, the data is available everywhere, so it makes reads more convenient and faster. A more scalable approach is a partition cache, which introduces a notion of data ownership. So if you look at this diagram, every node owns its own piece of data, and collectively across all the nodes, you have your total data set. So the more nodes you add, the more data you can cache. And you can also consider, for redundancy purposes, you can also consider adding backups to your data. So you can also have backups equally distributed within your cluster as well. So in partition mode, whenever you make a change, only the primary node is updated, and afterwards the backups are updated. So if you have, let's say, one primary node and one backup node, one primary copy and one backup copy, as shown in this diagram, any update to a single key will require 2 network trips, one to a primary copy and another to a backup copy. And if you have 10 nodes in your cluster, you'll have 2 network trips. If you have 1,000 nodes in your cluster, you'll still have only 2 network trips. So updates in a partition mode are very cheap. Reads, however, can get more expensive because data is not readily available on every node. However, that problem is mitigated by introducing near caches. Near caches are smaller local caches on a client side, which cache a portion of the data locally on the client side, which makes reads on the client side, reads of the same key for the same keys on the client side very fast. Just local memory, the reference. generally speaking, you would probably use both. Some of the data like that is doesn't change too much. Maybe partition data or maybe lookup data or reference data, you would generally put into a replicated cache. In partition cache, you would actually put data that grows and changes very fast. And a typical deployment may involve maybe 5, 10 replicated caches, 20, 30 partition caches. The important thing here is that you can transact between these caches at will, and you can query these caches at will. So you can do distributed joins between the data that's stored across multiple caches. It could be multiple partition caches, multiple replicated caches, or any mixture of thereof. If you have partition and replicated caches in the same query, the queries you should not worry about collocating or not collocating data for performance reasons, because replicated data is available on every node and queries will always work fast. So essentially, if you're familiar with the star schema, replicated caches look very much like dimensions, and partition caches look very much like facts. And if you look at it that way, then you can actually say that Ignite directly supports star schema as well. Probably talked already too much about SQL. Again, all SQL goes. All queries are fully consistent. All queries are absolutely fault tolerant, regardless of which failure happens within the cluster during query execution. All the indexes are in memory, and we strongly recommend that you index as much as possible, especially for the data that you will be using in your where clauses or in your joins. If you do that, then you'll get into nanosecond to millisecond query response time, and you'll be able to run thousands of queries per second on your cluster. And finally, I should mention that all the aggregations and group bys and unions and ordering, all those functions and keywords are supported. So you should feel absolutely free to run ad hoc SQL on top of Apache Ignite cluster. Here's a basic example of a query. It's very primitive, but at the same time shows quite a lot. We're doing a select over two tables, organization and person, and we're selecting, they're joined by organization ID, so multiple persons can work for the same organization. And so we want to query for, let's say, for average salary, max salary, and mean salary for all organization. And so in order to do that, we execute a join between person and organization tables. We do group by organization name, and we order by organization name. So this will actually provide a good summary of all the salaries across multiple organizations. Basic query, but yet demonstrate the power of SQL. In an ideal world, org ID in both classes, person and organization, should be indexed. The way this SQL actually looks in code is that we have person class and organization class, which means that person class becomes a person table for your SQL, and organization class becomes organization table. And all the class fields become columns for your query. So if you think about it that way, then you can easily project any kind of class relationship onto SQL query. So let's take a look at how Ignite integrates with Spark and Hadoop before we do a demo. First of all, I should mention that if you're running Spark or Hadoop, you're probably using Yarn or Mesos. Ignite easily integrates with both. So if you use those cluster resource managers, you can natively plug Ignite cluster into those environments. On top of that, I should also mention that Ignite supports Docker as well, so you can easily unwrap a Docker image and run Ignite in any environment. All right, so let's take a look at shared RDDs. As I mentioned, Ignite essentially provides a common memory layer across multiple Spark Spark workers, if you will, or Spark executors. And every cache in Ignite can be wrapped into an RDD. And there are various ways you can actually deploy Ignite. You can deploy Ignite as a standalone separate cluster and provide and access it in a client-server fashion. So in that case, a Spark RDD will make remote calls to Ignite cluster. You can actually deploy. You can also deploy Ignite in a more of a collocated fashion, directly in the same JVMs as your Spark executors, Spark jobs are running, or on Spark worker nodes as well. So by doing that, you can actually provide in JVM kind of data access, which will be much faster because you simply will be dereferencing pointers. However, you'll be reusing the same resources for Ignite and for Spark. So that's something you have to consider if you can allocate some extra memory in your Spark projects or Spark deployments for caching Ignite Spark RDDs. Then you should definitely consider a more collocated approach. And so this approach actually allows you to share state between Spark, between multiple Spark jobs and Spark tasks, because you can easily access the same Ignite RDD from different processes, from different from different Spark processes, different Spark nodes, if you will. Ignite is very good about sharing data, so that works out of the box. However, as a bonus, as I mentioned before, you also get faster SQL. So you can run, you can index data, you can index data that resides in your RDDs, and you can then actually query it very fast, including execution of distributed joins. There are several main abstractions that you should be aware of when working with Ignite and Spark together. The main entry point into Ignite RDDs would be Ignite context, which, as you see, receives Ignite configuration and Spark context as a parameter. So we will, whenever necessary, delegate to Spark context, and we'll use Ignite configuration to start up an Ignite node, either in client or server mode, directly within Spark process. Another important abstraction is the RDD itself. So once you actually created Ignite context, you can create an RDD over any cache that you defined within Apache Ignite. This is how the code will look. Essentially, you execute from cache method, and it returns an RDD. And as I mentioned, RDD is mutable, so we add a few methods in addition to supporting Spark API, Spark RDD API natively, we also add a couple of methods to support mutation and SQL. So save pairs method will actually provide ability to alter the state of the RDD. You can use basic Scala there, as you see, and you can use Spark context to parallelize and basically any method on the Spark context is available. And as a result, you can also execute SQL on top of cache RDD. And this how SQL will look like. I mean, a basic JDBC syntax, you pass in parameters, and you get a result from SQL execution. The result itself is a data frame. So once you got the result, once you executed a query over Ignite cache, you can actually then post-process the data using native Spark DataFrame API. Another way to share state across multiple Spark jobs and applications is by utilizing Ignite in-memory Ignite file system. The Ignite file system is native, implements Hadoop file system API, so it's natively interchangeable with HDFS. You can easily place it on top of HDFS by simply changing Hadoop configuration, and without changing any code. your Hadoop will now work over an in-memory file system. And optionally, whatever changes you make to in-memory file system, you would also persist, Ignite can also persist automatically to HDFS file system as well. So how do you decide when to use which? Well, I would say that if you're natively working with objects and you need to access them using native Spark RDD API or SQL API, I would recommend using RDDs. If you're working with files, sometimes you really you're working with log files or PNG files, then you should probably consider using in-memory file system. Either way, the data will be cached in memory and the data will be provided very fast. And either approach will give you a good acceleration and scalability boost whenever integrated into your Spark applications. One more thing I should add, I don't have a slide for it, but Ignite also provides an implementation of Hadoop MapReduce in memory. So if you integrate Ignite MapReduce and Ignite file system into your Hadoop application, and it's just a plug and play integration, there's no code to change, you'll get a very good boost, performance boost for your Hadoop cluster. So if you're still using MapReduce or Hadoop, this actually gives you ability to accelerate those clusters without changing a single line of code. However, I do recommend if you're starting new projects, do consider using Ignite with Spark, because it provides you much better abstraction. Spark provides much better abstractions and much better performance than you would get out of your MapReduce, native MapReduce APIs. So what's ahead of us? What are we planning to do with Ignite? Number one, I should say that we recently added a very important feature called non-collocated joins. Essentially, you do not need to worry where your data is stored in order for your query to execute. However, you should keep in mind that if you properly collocate the data, the queries will execute faster. However, it's not always possible to collocate. That's why support for non-collocated joins is very important. However, you should still continue to at least make the best effort to try to collocate as much as possible for performance reasons. We are also adding various DML commands to our SQL capabilities. So far, Ignite has been supporting everything that starts with the word select. All the data modifications have to happen through key value API. However, very soon in the upcoming release, which is within a month, we also are adding support for insert, update, and delete commands. So you'll be able to interact with Ignite virtually without writing any Java code, if that's your use case. By the end of the year, we also plan to, there's a typo, it's DATA, DATA, definition language, DDL. By the end of the year, we plan to add support for DDL, which will add commands like create, alter, and drop. So you'll be able to create tables and indexes dynamically using standard SQL commands, which will make Ignite completely available, completely usable, I would say, without writing a single line of Java.NET or C++ code. You'll be able to create various database schemas, populate them, and start querying them in a distributed fashion. So in addition to in-memory DataGrid, Ignite will also support in-memory database functionality. We also continuously improve our IGFS performance, Ignite file system performance, and we're actively working on better DataFrame integration with Spark. So you could actually take various portions of your query and also execute them on top of Ignite cluster as well. And now I want to hand it over to Valentin, who will be doing a demo. I'll give a little bit of a description. So we will be using Ignite. We'll be using Apache Zeppelin for the demo, which provides a nice visual graphical interface for query execution. And Valentin will run identical queries in Spark and in Ignite, just to demonstrate the performance difference basically between having indexes and not having indexes when you execute a query. So Valentin, please take it over.
Thanks, Dmitry. Hello, everyone. So I will make the quick demo. As Dmitry said, I will basically use the Apache Zeppelin to execute a couple of queries and show the difference in performance between executing them in Spark and Ignite. But first, let's go through the data schema that I'm using in this demo. It's very basic and simple. So I have the organization table. In Ignite, we use organization class, and it also has these Ignite annotations, which basically configure the queryable fields and indexes in Ignite.
Valentin, can I interrupt you for one moment? We're being asked by the audience to zoom the screen or make it a little bit bigger. It's hard to see.
How I do that?
Just increase the font, Valentin.
Yeah, that's what I'm trying to do. Better now?
Oh yeah, that's great.
All right. So this is the organization table, and it basically just has the the organization ID, which is kind of a primary key for this table, and organization name. And the second table is the person table, which has several fields. So first one is also the ID, which is also the primary key for this person. The person name, and also the organization ID, which actually links the particular person to the organization it belongs to. We will use this as a foreign key when joining two tables with each other. Additionally, it has the manager ID field, which basically links the person to another person, which is the actual manager within the organization. So if it's this field is nullable, so if it's null, it actually means that this person is the manager and it doesn't have its own manager. And also it has the salary field, which just defines what salary this person has, this employee has. All right, so let's now go to the Apache Zeppelin. Should I do it larger as well?
Yes, please, if you can. Great, great, thank you.
Okay, so I have all the data preloaded, both in Ignite and in Spark. So but we'll skip this step, and I will run a couple of queries over this data set. So the first query basically just joins the person and organization tables. What is that? By the organization ID field. It also filters out by organization ID. So we are interested in results for several particular organizations. We also group by the organization name and calculate the average salary for this organization within this organization. And we also order by the salary, by the average salary. So this is the Spark notebook. So I'm executing this query over the Apache Spark. So this basically takes a while because Spark doesn't have indexes and it has to scan all the tables that are participating in the query. So it took like 16 seconds. The data set is rather small, by the way, just a couple of 2 million of organizations. It fits on my small laptop. The second query is a bit more complicated. It has two joins. So as a previous one, it joins the person with organization by organization ID, and additionally, it joins the person table with itself by manager ID. And then it selects organization name, employee name, and the manager name of this employee. So basically, what it does, it returns all the employees for the particular organization, telling what manager each employee has. So let's execute this one. So as you see, it actually takes even longer, mostly because of the second join that we have here. Still running. It's almost done. Okay, so it took almost a minute, 51 seconds. So now let's go to Ignite notebook, and I will basically run the exact same queries over the Apache Ignite. So we have the special interpreter in Apache Zeppelin. So you just type ignite.ignite SQL here, and then you just provide your SQL query, and it will connect directly to the Apache Ignite cluster and execute a distributed query against the Apache Ignite cluster. So let's execute this one. This is the first. As you can see, this is the same exact query. It joins person and organization, groups by the organization name, and calculates the average salary for each organization. So let's execute it on Ignite. So as you see, it's much faster than with the Apache Spark. I can also change some data here, like say select this for different organizations, for example, like that. And it still takes a couple of seconds. And the second query, again, the same exact query that we ran with Spark, and as you can remember, it took 51 seconds there. And with Ignite, it's just, it's very fast. So basically, it shows 0 seconds, which actually means sub-second latency for executing this query. I can also, what's going on? Excuse me. I basically want to change something here. So say, do the same execution for a different organization. So we see that the result is changing, but it's still very fast. So, so as you see, since Ignite has in-memory indexes and Spark doesn't, Ignite doesn't have to scan the whole tables. And basically, even if we increase the data set, the performance in Ignite will not change a lot, which is not true for Spark because it will still have to scan all the tables, and with a larger data set, it will be more data to scan. All right, I'm done.
Thanks, Valentin. Alyssa, are there any questions?
Hi, yes, there are several questions, so I'll go ahead and ask them. The first one is a single RDD replicated across multiple Spark nodes to facilitate failover? How is this replication factor controlled?
So the question is, how do we make sure that Ignite, that RDD is resilient to failures, essentially? In Ignite, if you remember when I was going on showing the slide for Ignite context, one of the parameters into Ignite context was Ignite configuration, where you would simply specify a number of backups to equal 1, 2, or 3, or however many copies you want of backups you want in your cluster. So if you configure one backup, then your cluster will be resilient to one server failure. If you configure two backups, then to two server failures, etc. So the answer is yes, backups are supported, and you will control them by setting a configuration parameter in your Ignite configuration class.
Okay, the next question. Does the off-heap option run outside the purview of the JVM using the RAM outside the JVM heap?
Can you repeat the question? You disconnected initially.
Sure. Does the off-heap option run outside the purview of the JVM using the RAM outside the JVM heap?
So essentially, the question is asking how, where is off-heap memory located, and whether JVM knows about it. So the answer is off-heap memory is outside of main JVM memory. So JVM does not know about the memory allocated off-heap. However, the access to that memory is as fast as you would have internally within JVM. So given that the data management, data manipulation on Ignite is very controlled, essentially you have certain commands for or API calls for data updates or data reads, we can easily control the lifecycle of the data stored off heap, so we can do our own collection of the memory whenever you remove your data from cache. Until you remove your data or change your data, we actually keep the data in memory, and we don't have to worry about collecting it. So the memory management, whenever it comes to DataGrid, is a lot simpler than JVM would impose on a general object garbage collection. So that's why using off-heap memory is many times going to be faster than using Java heap. Data is still one pointer away. However, whenever you store lots of data, or maybe your indexes grow too big, it's very important to make sure that you put them outside of main Java heap, because garbage collection on the data set beyond 10, 16 gigabytes requires significant tuning and often may take half a minute to a minute. On a cluster of, let's say, 10 nodes with 50 gigabyte of memory, GC pause may take up to 5 minutes. So it's very important that you take advantage of the off-heap functionality.
Okay, the next question. How does Ignite compare to MemSQL, which is an in-memory distributed database? Do you see them handling different use cases, or do you see Ignite on top of MemSQL, or is that redundant?
So the question is, how does Ignite compare to MemSQL? And whether they should be used together. I would say that probably there's I see very limited use case for using Ignite and MemSQL together, one on top of another. I think the main difference you'll find is that Ignite, as I mentioned, supports multiple ways to talk to your data. MemSQL generally supports only one. It's SQL. You can use SQL with Ignite, and you can connect to Ignite also using ODBC and JDBC drivers, which we provide. However, what about key value API? What about MapReduce or compute APIs? What about collocated processing? What if you want to send a computation exactly to the node where the data resides, essentially to avoid any redundant data movement? Or what about subscribing for a basic event subscription? Maybe on client you want to receive event notifications whenever your data changes on the server side. So all those things are not possible with direct, or very difficult to implement directly with SQL. And in Ignite, they're natively supported just by utilizing our API.
Okay, next question. Spark also stores the data in memory, so what is the extra percentage of memory requirement?
So Essentially, that's a good question. Spark stores data in memory and Ignite stores data in memory. So the difference here is in Ignite, usually if you choose partitioned distribution model, data is partitioned across multiple nodes. But there is a certain overhead of that you have to account for because Ignite data is going to occupy some memory. So if you cannot feed it directly onto your Spark cluster nodes, you should deploy Ignite as a separate cluster and access it in a client-server fashion. If you can allocate certain memory to Ignite, a certain chunk of memory to Ignite on the same JVMs as Spark, then you can also deploy it together on the same servers as Spark and probably have less network traffic and even better performance. Memory overhead is something that cannot be just measured, cannot be just given. Like we would have to, usually you come up with it by populating Ignite cache and actually looking how much data you're storing and how much data that does it occupy in Ignite. So you usually get to the overhead from direct testing.
Okay, great. Next question. Right now, Spark data frames need to be converted to RDD pairs before saving to Ignite. That's a question. Are there plans to support to save data frames and data sets to Ignite without converting to RDD pairs?
Yes, so there are certainly plans, and we're actively working on it. My hope is by the end of this year we'll have full data frame integration. Essentially, the data frame integration that that was asked about. You'll be able to utilize Spark RDDs directly without converting them to Spark data frames directly without converting them to RDDs.
Okay, next question. Does Ignite provide its own connectors to NoSQL databases, or is it Spark specific to create RDDs in memory?
So the question is whether Ignite has various connectors to various databases, as NoSQL database. I would say this, that your Spark RDDs or Ignite file system should be used only whenever this integration, this type of API makes sense. You can always natively use Ignite APIs directly from Spark. There's nothing that prevents you from just calling and executing code over Ignite caches directly. The RDD API is simply provided for convenience. And when you're using Ignite caches, then you get native integration with databases like Apache Cassandra, or all the RDBMS databases like Oracle, MySQL, Postgres, MySQL, etc. Probably forgetting quite a few. So all of that is natively supported in Ignite without writing any additional code.
Okay. Are there any plans to support Scala API for Ignite?
Ignite already has support for Scala. There is a Scala component available in Ignite that you could utilize. However, in my view, in the recent versions of Scala, they made a lot of progress, and using Java APIs directly from Scala is becoming more and more natural and much easier than it used to be before. So a lot of our users, actually, when utilizing Ignite from Scala, will take that option and start just using native Ignite Java APIs directly from Scala. However, there's also a Scala DSL that we provide that you could take advantage of and see if it fits you.
Okay, next question. What is the best deployment option for Ignite and Spark when used together?
Well, as I mentioned, there are several deployment options. One is co-located with Spark service, another is having Ignite as a separate cluster. I think, the main consideration here would be memory consumption directly on Spark nodes, and whether you want to store data essentially on your processing nodes. There are some users who will require an extra degree of separation, having a data cluster separate from a processing cluster. And in that case, Ignite would be deployed separately. However, the query execution does not suffer regardless of whether Ignite deployed in a client server or client server fashion or directly in collocated fashion where servers are collocated with Spark nodes. So the queries are still going to be fast. Accessing data from RDDs may be a little slower in a client server fashion because it has to be fetched. But it's still going to be pretty fast regardless of the deployment option you use. So I would say mainly the main consideration would be if you have enough memory to collocate Ignite cluster with Spark cluster, I would collocate them.
Okay, and we have time for probably one more question, and that is, how do we measure memory usage sharing between Spark and Ignite process?
Well, I mean, Spark is a JVM-based. Spark usually runs in Scala, so it's a JVM-based environment. So you can basically allocate any type of pass any type of memory you want to allocate for Spark for Spark JVM as the parameter. And same goes for Ignite. For if you're using off heap option, then you can also add amount of memory you would like Ignite to use outside of JVM heap. So essentially, collectively, you have a full control over all the memory used by Ignite and Spark, and it's up to you how you want to split that up. I will tell you this: the more you cache, the more data you cache in Ignite, the better performance you will eventually get.
Okay, great. Well, that brings us to the top of the hour. Dmitry and Valentin, I want to thank you for a great show. And audience, thank you so much for your participation. We had lots of great questions, and I hope to see you on a future webinar. With that said, everyone have a great afternoon or morning or even evening, depending on where you're calling in from, and we'll see you again soon. Thanks, guys.
Thanks, everyone. Bye-bye.